Good morning, everyone.
Good morning.
So today we continue coding. We don't have much work left for us to do. And I hope soon we're going to see some results. So I'm going to share my screen now. Do you see my screen?
Yes.
Okay, so this is the code we've been working on. Do you remember what extract XY was? That's what the last thing we did.
Just get all the data that you put in, get it out. Yes.
Again,
you extract a matrix, actually two matrices.
Yes, it's just reorganizing the data set into two matrices, right?
Yeah, okay.
You remember the dimension of X and Y?
You changed it. So in the beginning, X was a vector, a long vector, 120,000 long vector. Then you did something, didn't you? And Y was two, only two.
Right, but now it's matrices. Those are matrices.
Yes.
So K is the size of the data set, 200 pictures.
Yes. No. 120,000 is just for one picture.
Exactly, yes.
Now you multiply it by 200, if I remember correctly. Okay.
Yes. Okay, fine. So we already written we wrote the train function, but we didn't implement the calc gradient, right?
Calc is calculate, right?
Yes, but I was thinking about it. Let's do it. First, we'll do it numerically. It's much easier.
Yes, sure. Numerically is just take the last point, the one before last, and go and take the difference, that's the derivative.
Yeah, like it's, we'll see. Okay, so just a minute. I'm gonna, we'll define this function, and I will add a default parameter, which will be the epsilon, which will be the delta we're gonna be using for the numerical calculation, okay?
Okay, yes.
This is like 1 millionth, right? Okay, so what do we need to do? We need to return a gradient, and we call it dw.
Yes.
And what's the dimension of dw? The same as w, right?
Same as w, of course. It's a difference between two w's.
So
yes.
the easiest way of doing it is NP empty like. When I say like, it's like construct an empty matrix with the same dimension as W. Okay?
Very, yes, efficient, yes.
Yeah. Actually, every code that we do to NP, instead of doing it ourselves, is much more efficient because it's implemented
Already,
in,
yes.
Yeah, it's a machine language code, actually, Rapsi. Okay, so now I need to run over all the elements of W and calculate the partial derivatives. So I will make a loop for I in range. Do you remember what the size of W, the dimension of W?
W is the coefficients of your,
Exactly.
so it's the same thing, same dimension as X.
Not exactly. Let's go over.
It multiplies X, doesn't it?
We're dealing with matrices and multiplication of matrices, right?
Yes.
So
right.
The function f of x is now x will be all of them. It's w x, right? This is the matrix multiplication, and here we have softmax.
Yes. Okay.
So
The softmax doesn't change the dimension.
yeah, it doesn't change right. It doesn't change the
You do it
dimension.
entry by entry, right? The softmax.
Yeah,
Do
yeah,
exponentiation entry by entry.
yeah,
That's the same.
right. But let's see, the dimension of x now is n over k. This is x, and the w, the coefficients, it should be n
Uh,
and by 2, right? Because at the end, we want to have 2 by k, right? Which is
right. Okay.
probabilities, right?
Mhm.
Okay. So, so W should be n 2 by n.
Okay.
Okay.
Mhm. Okay.
Are you with me or?
I think so. Yes.
Okay. This
Okay.
I will. I try to make a sign for matrix multiplication. Never mind. So okay. So in range, so I should move in the range of 2. It's the dimension of W, and for J in range of N. And let's write here that the dimension of W is 2 by N.
Mhm.
Okay, now I want to numerically calculate the
Derivative.
derivative. So I would like to make a copy of W, because I'm going to change it and I don't want to ruin it. So I will define a new matrix, which will be just a copy of the old one.
Okay.
You're going to see why, because I'm going to change it.
Mhm.
And now I would like to change one element and add it in epsilon, because I'm trying to calculate the derivative. So W2 at the place of I and J, that's the element that I'm dealing with. I'm
Mhm.
going to add it. Remember what that means?
Yeah. So you just add to the existing one. Yes.
Yeah, exactly. So, but before I'm changing it, I want to calculate the loss before the change. So L1 will be loss of X sig Y sig WT before the change.
Yes.
You remember that?
Let's recall what is the loss. The loss is
uh,
how off you are, how far you are from the
Yes,
given
actually I
training.
didn't implement it yet, but loss, we're gonna, loss will be, we define loss of W. Yeah, it's the distance between the function, between the prediction of F and
Real
the
life.
cloud of points, the data set. So it was something like that, if you remember.
It shouldn't be K there. It's the number of
You're right.
1 over K.
Yeah, it's K. Thank you. It's K, and this is like small k, 1 to big K, and it's, you remember, it's cross entropy.
Yeah, I don't remember, but you'll have to remind me.
It's YK. So it's, and this is the F of XK.
Okay.
That's the way we define
HK should
the
have two variables, no?
H
Cross
has
entropy
two
is
variables. One is it's just a matter of notation. This is one of them, and this is the other one.
Sorry, what? Ah, okay.
It's
So
just a
y
notation
appears
for
there. So
context.
implicitly, y appears there. The real y.
Yeah,
Yes.
yeah. Yes, yes. Okay, so let's do it. We didn't implement loss yet, but we'll do it later. So L1 will be the loss before the change, and we'll do the same after the change, right?
Uh-huh.
This we'll call it L2. This is after the change. And
So
now,
1 minute, please. Loss,
yeah,
just a number?
yeah, loss is a number.
Just a number. How far, it measures how far you are from the training picture.
Yeah, it's actually the average of the distances, but
Yes,
it's
yes.
a single number. Yeah, it's important.
Single
Loss
number.
is always a single number.
Yes.
Yeah, a real number. Now I know what's the dW of I and J. It's, can you dictate what I should write here?
dW is W, W2 minus W1 over epsilon, but
L2 minus L1, right?
L2 minus L1 is how far, yes, you measure whether you got nearer or you got further, and how long did you get nearer or further?
We're dealing with a D loss for D W I J, right?
Yes.
That's what we're trying to calculate, right?
Yes, yes.
That's the partial derivative. So does it make sense what I've just written?
Yes. Okay, yes.
So it's...
So 1 minute. So yeah. I don't see on the right how it depends on I and J. It's just the loss. It does not have variables I and J.
Look, I've changed in W2 only the element of IJ. That's the only element I've changed.
You do it one by one, I guess. Okay.
Yes.
This is very strange that you do it by one, but okay.
It's strange that I'm doing it one by one. How would you do it?
I don't know, change.
Because partial derivatives,
yes,
if you want to calculate it.
Okay, okay.
Right, partial derivative, you need to change only one element and see the effect, right?
Okay.
Okay, so those two loops of line 3 and line 4, altogether they will calculate the whole DW matrix, right?
Yes.
Okay, so all is left for me to do at the end is return DW, right? That's what I wanted.
Yes, okay.
Which is a matrix that represents the gradient. Yes. Let's see how we called it. You remember we called it, we wanted only DW from that algorithm. Okay, but we didn't implement loss yet, right?
You didn't write what it is, yes, okay. But,
so let's do that also. We'll start by F. Def F. F receive W and X. Remember, we're dealing only with matrices now. So,
are you defining now F or what?
Yeah, I'm defining F. I didn't do it in, I've never done it before.
And so, F is the loss, or what is F?
F is this.
The real F, yeah, okay. The old F, okay.
This is what we're going to call the neural network, even though it's just a function, yeah?
Okay.
So F will be just, you remember that's the way we
multiplication of matrices, yes.
Yeah. And I will call the value of this matrix multiplication logit. It's not a name that I invented, it's a convention. Because in deep learning, everything before softmax is called a logit value, but it's never really matter. Now I need to do softmax, right? Right? F of x is softmax of that. And softmax is just exponent and
dividing by
normalization, right?
Yes.
So let's first do the exponent, and I do everything matrix-wise. So NPX is just, this is a NumPy way of doing element-wise e to the power of the entry. Okay? Is it clear or not?
No, it's clear. Yes. Okay.
Okay.
That's
now
softmax.
I need to do something like that.
Okay.
Why are you laughing?
Because this language is very, we call it,
Very peculiar to you?
Very effective.
Yeah. Very effective. Let's see what I did here. I need to think about it if it's correct. I wanted to normalize it, okay? X sum should, let's write dimension so we won't be confused. What's the dimension of logit? You remember? It should be 2 by k, I see.
2 by k, right? Yes, for every picture. Yes.
This is 2 by k. This is also 2 by k, right?
Yeah. But you're just normalizing the vector now. You're not doing anything.
Yeah, I'm not doing everything. So anything. So yeah, 2 by k should be. The only thing I'm not sure. I'm thinking whether I should do something like that. I might be needing to tell him what kind of a summation. How do you say that?
Summation, yes. Coming up, yes.
I want to know if I need to sum only the columns for the normalization.
Separately, you normalize each separately, of course.
Yeah, right. So let's do a little experiment here. Let's define a matrix, a NP array, like a toy matrix, 1 by 2 by 3. I just want to make sure that I'm doing the right thing. 4 by 5 by 6.
What is it?
This is a matrix, right? A is a matrix with 2 lines.
So it has 2 rows?
It has 2 rows and 3 columns. Okay. Now, let's ask him what's the sum of it like that. I think it will sum all of it. Let's see. Oh, he will say that I don't have NumPy. You know why? Because I didn't run everything. He doesn't know NumPy. So let's run, I need the import. I didn't run the code yet. So I will run import NumPy, okay? In order for us to have NumPy available. So let's go back. We were here. 21, it's not what I wanted, right? 21 is the
sum of everybody, yes.
Yeah, what I would like is the sum over the columns.
So you want a vector of size 3.
Of size 3,
5, 7, 9.
Exactly. Let's see if that's the right right way of doing it? Yeah, that's what we wanted, right?
I didn't understand what his axis is 0.
Yeah, it's the dimension. Let's put 1 here and see what's happened. It's
what's this?
6 is the sum of all of these, and 15 is the sum of all of these. This is summing over the other dimension.
Okay.
Which we don't want. We want this.
Okay. Send it the command axis. Okay.
So that's what we really want, right?
Right. Okay.
Okay, so I'm normalizing, I'm dividing each element by the proper sum. Is it correct? Let's see. This operation is an element-wise division. Does it make sense?
You want to divide these vectors, the 1 and the 4, you want to divide by 5?
Yeah, exactly. I want to divide 1 by 5 and 4 by 5.
Yes.
Exactly. I'm not entirely sure that I did hear something correct, so I put some question marks. I will think about it later, okay?
Okay.
I'm not sure. But now let's implement the loss. The only thing that I'm not sure of is this division here. I will think about it. Okay. So def loss, what does loss need to get? Loss need to get X, Y, and W, right?
What?
So let's see. And we already implement F. So again, this was the formula for the loss. So let's think about it. We need to NP dot first. Let's write the formula for cross entropy. You remember the formula for cross entropy?
Just sigma of 1 over yi log xi, something like that.
Something like that, yes. It's a binary. It's binary probability, so it's a log. Oh, sorry. It's a y1 multiplied by log in the base of 2 of x1.
Yes.
I forgot minus at the beginning. I'll put it later. Okay. This plus, it's a very simple formula. Okay, and this is x2. All this minus, okay? So what will be the easiest way of doing it matrix-wise?
1 minute, what is x1 and x2? Y's are the real values, right? The measure, the values, the real cat or dog vectors, right?
Cross entropy gets 2 probabilities. In our case, 2 binary probabilities. This X, I might have chosen the wrong letters, but This is actually,
okay. So you've just defined to me, you're going to implement it with our parameters. But this is just
yes,
the definition so that I know what you're speaking about. Okay.
yes, yes. Okay, so let's see. NP log 2 is the way of calculating log of with base 2 in NumPy. I need log of x2 in and I need to multiply it element-wise by y. I do it matrix-wise, but it makes sense, I think. Let's call that, I don't know, 10th matrix. And all I need to do, I think, is all again return a temp sum. I think this will do the job. This is not matrix multiplication. This is element-wise.
Point by point, yes.
Okay. So does it make sense? So I multiply element-wise y with log in base 2. What about the minus? I forgot the minus. Let's do the minus here, right?
Mm-hmm.
I think that should be working. Does it make sense to you, or is it hard to follow?
No, it's not hard to follow. So it's just, we should remember that this entropy measures how far x and y are, right?
Right.
Entropy,
Yes,
cross entropy.
we use this cross entropy as a measure for distance between two probabilities. In
Yes.
our case, two binary probabilities.
Yes.
They are binaries because we are constructing a classifier only of two classes. If we had more animals to distinguish from, it would have been a more
Yes, okay.
yeah. Okay, we're almost done. The only function, this is, we call it loss. We already implemented loss. So we have this implemented. The only function we didn't implement yet is this, which is extremely simple. Okay, you remember what that is?
Status or epoch or what?
Yeah, it's just the printing for
Epoch
the.
is to how much, how often you measure it. Yes, how often you look at the results.
Let's implement it. Def. So let's do something really naive here. Just f will do we'll just give the user information about the epoch and the loss. That's it. Now everything is ready. We can run it.
Hopefully.
Let's. I want to check it, double check it before we run it. So I think that's a good place to stop now.
Okay, so
We're in the middle of the tension.
you have a whole day to check. Okay.
Okay. So thank you, Ron.
See you.
Yeah.
Uh,
Just a minute.